Let us use L'Hopital's rule to determine the limit of the following functions. It says you can use a graphing utility. I will not, but we will get the limit. If you have a graphic utility, you're welcome to use that. Let's see. So here, the limit as x goes infinity of x times the tangent of 1 over x. Now, as x goes infinity, 1 over x goes to 0. And so here we have the tangent of 0. Well, tangent is the sine over cosine, so it gives us 0 over 1, so it gives us 0. And so here we have x goes infinity, we get infinity times 0 for our indeterminate form. So if that be the case, then we apply L'Hopital's rule, and you have to write it in the form of L'Hopital's rule. Let's see. So this is the limit as x goes infinity of tangent 1 over x divided by 1 over x, because 1 divided by 1 over x is x in the numerator. But this is of the form of the limit of f of x divided by g of x, where f of x and g of x, that ratio with the limit is said to be in an indeterminate form. Well, if you check that again, this is the tangent of 1 over x as x goes infinity. This is the tangent of 0. So this gives us, the tangent of 0 gives us 0. And this is here 1 over x as x goes infinity. That gives us 0. So here we get 0 divided by 0. Again, it's indeterminate form. And so if that's the case, then we can take the derivative of the numerator and the derivative of our denominator. Let's see. So this is the limit as x goes to infinity. This is tangent of x to the negative 1. So this is secant squared of 1 over x times the derivative of 1 over x, which is x to the negative 1. Take that derivative, we get negative 1 over x squared. All over the derivative of 1 over x, which again is negative 1 over x squared. Well, those terms cancel out. So we have the limit as x goes to infinity of the secant of 1 over x, secant squared of 1 over x. Now secant is the 1 over cosine. We can just write that as such. This is 1 over cosine squared of 1 over x. Now 1 over x goes to 0 as x goes to infinity. Cosine of 0 is 1, so we get the limit of 1. All the wasted space. Let's check this. This is the limit as x goes to infinity of x to the 1 over x. So this is in the infinite term here raised to 1 over infinity. So this is infinity raised to 0. In indeterminate form, right? But to do L'Hopital's, we need to be able to bring down this 1 over x as a power. We can use something from the natural log properties. We know that the natural log recall that the natural log of x to the m is equal to m times the natural log of x. So if that be the case, then we say here let y equal to the limit as x goes to infinity of x to the 1 over x. Now let's take the natural log of both sides. So the natural log of y is equal to the natural log of the limit as x goes to infinity of x raised to the 1 over x. Now here, as x goes to infinity, we have continuity, so that it is safe to say that we can take here the natural log of the limit is tantamount to the limit of the natural log. So we have the natural log of y is equal to the limit as x goes to infinity of the natural log of x to the 1 over x. Now we take this term. This is the limit as x goes to infinity, and you can write this as 1 over x times the natural log of x. Now let's see, what do we have in terms of checking to see if this is an indeterminate form. Well, this is 1 over x as x goes to infinity, so this gives us 0, and then this is times the natural log of x as x goes to infinity. This is times infinity, so here we get 0 times infinity, another indeterminate form. And so if that be the case, then we apply L'Hopital's rule. So here, this is the limit as x goes to infinity of the natural log of x all over x. Let's check. Is that in the form of L'Hopital? Does it meet the description? You got to have indeterminate form. So this is natural log of x divided by x. As x goes to infinity, you get infinity divided by infinity. So if that be the case, we take the derivative of the numerator divided by the derivative of our denominator. Well, the derivative of the natural log of x is 1 over x times the derivative of x. That just gives us 1, divided by the derivative of x. That gives us 1. So this is the limit as x goes to infinity of 1 over x. Now as x goes to infinity, 1 over x goes to 0. But you recall that we started with, this is the natural log of y. This is the natural log of y, right? This is all equal to 0. And by definition, if and only if, well, think about it, this is the log of base e of y equal to 0 if and only if y is said to equal to e to the 0, which is 1. But what was y? Y was the limit at hand initially. So we conclude that y, which is the limit as x goes to infinity of x to the 1 over x, gives us 1. Let's consider this problem. And this is number 51 Oh, and number 52. Look at the similarities. Now they're the same except how x tends. For 51, x goes to 0 from the right, and then number 52, x goes to infinity. Well, this will be interesting to see how that works out. You plug in 0, here we get 1 to the, now as x goes to 0 from the right, if you examine this 1 over x, so as x goes to 0 from the right, this 1 over x goes to positive infinity. So here we have 0 raised to the infinite power. So here this is an indeterminate form, and if that be the case, then we apply L'Hopital's rule. Again, you got that 1 over x in your exponent, so you'd better to pull it down to use the natural log. So same argument from before. Let y equal to the limit as x goes to 0 from the right of 1 plus x to the 1 over x. Take the natural log both sides without loss of generality. This is the natural log of the limit as x goes to 0 from the right of 1 plus x to the 1 over x. This is the natural log of y is equal to, here, as x approaches 0 from the right, not at x equals 0, but as x gets close to 0 from the right, this function is indeed continuous. So we can switch the positions of the limit and the natural log, and we get the same value. Here, this is the limit as x goes to infinity. Oh, well, not x goes to infinity, but x goes to 0 from the right of the natural log of 1 plus x to the 1 over x. So this is the natural log of y is equal to the limit as x goes to 0 from the right of 1 over x times the natural log of 1 plus x. So when you check that for an indeterminate form to be able to apply L'Hopital's rule, let's see. We have the natural log of 1 plus x as x goes to 0 from the right. This gives us the natural log of 1, which is 0, divided by infinity. So here this gives us 0 over infinity, again, an indeterminate form. So we have the natural log of y is equal to the limit as x goes to 0 from the right, and this is, yes, the natural log of 1 plus x. You just write that over x. Apply here L'Hopital's, so this gives us the limit as x goes to 0 from the right. The numerator, that derivative is 1 over 1 plus x times the derivative of 1 plus x, which is just 1. So this is just 1 over 1 plus x divided by the derivative of x is just 1. So we get the limit as x goes to 0 from the right of 1 over 1 plus x. Now as x goes to 0 from the right, 1 over 1 plus x goes to 1. There's no discontinuity there. Just plug in x equals 0. So you get 1 over 1, you get 1. But we started out with the natural log of y. This is equal to 1. If and only if e to the 1 is equal to y. And so we get y is equal to e. But what was y? Y was said to be the problem at hand. So here we have the limit as x goes to 0 from the right of 1 plus x to the 1 over x is equal to the e base number. Now let's see what happens with the same problem, but we send x on a different route. Instead of x getting close to 0 from the right, here x goes to infinity. So when you plug in x to be infinity here, this gives us infinity for the base raised to the 1 over infinity that goes to 0. So again, is indeterminate. Anytime you have an exponent with the term here, it's always good and safe to use the natural log. So let y equal the limit as x goes to infinity of 1 plus x to the 1 over x. Take the natural log of both sides. So the natural log of y is equal to, and since we've done this a couple of times, we can go ahead and kind of get right to it. This is the limit as x goes to infinity of the natural log of 1 plus x to the 1 over x. Always as you go, always check to make sure that it is applicable to apply the L'Hopital's rule. And the only way that you know that it's applicable is that the rational expression is indeed indeterminate. So, yes, so we have here the natural log of y is equal to the limit as x goes to infinity. Now we can bring this 1 over x down times the natural log, and just go ahead and just drop that x downstairs. So this is the natural log of 1 plus x over x. So this is the natural log of y is equal to, we can check indeed for indeterminate form here. As x goes to infinity, we have infinity divided by infinity. So we apply L'Hopital. So this is the limit as x goes to infinity. Take the derivative of the numerator. That just gives us 1 over 1 plus x divided by our derivative of our denominator, which is just 1. So we have the limit as x goes to infinity of 1 over 1 plus x. Now, as x goes to infinity, 1 over 1 plus x goes to 0. So we have the natural log of y equal to 0. That's if and only if e to the 0 is equal to y, and so e to the 0 is 1. So we conclude here that y, which was that limit as x goes to infinity of 1 plus x to the 1 over x power is equal to 1. Now it's interesting to note because this problem differs from the previous problem as x here goes to 0 from the right, and this next problem x goes to infinity. For the first one, we got the result to be e, the e base number, the natural number. And then for this next problem, all you changed was x tending. Here, this limit came out to equal to 1. So you want to be mindful of that, okay? Thank you. Thank you, my friends.